Alright, so today we're going to talk about physical state and phase change. So this might be a topic that's very familiar for most of you since you've been talking about it, I don't know, since 3rd grade. So hopefully this is an easier section and we'll just get to it. Alright, so first of all, when we talk about physical state, we're talking about solid, liquid, and gas. Okay, so that's all we're talking about. And phase change is just the change from one to another, right? So phase change will just be the change from either solid to liquid, liquid to gas, or back the other way. All right, so let's get to it. So before we can talk about that, we have to talk about the difference between heat and temperature. So these are words in the English language which we use interchangeably, but they're really not the same thing. So heat, another way to think about it is this is a total kinetic energy. Is a total kinetic energy of a substance, and temperature then would be the average. And remember, kinetic means moving, so it's the energy of movement. So heat is a form of energy. So if we go through this list, it's a form of energy. Right? It's measured in calories or joules. So the heat energy of food is going to be the calorie. And the way we measure calories, we'll talk about later when we have thermochemistry, is we burn the food. We measure the amount of kinetic energy or heat it puts off, and we give that the unit of calorie. Remember, there is no coldness. When you feel something that feels cold to you, what you're sensing is it has less kinetic energy than what is in your hands. Right? So you're feeling your kinetic energy being absorbed by the substance. Objects with temperature above 0 Kelvin, remember 0 Kelvin is what they call absolute zero, or molecules without motion, right? Has heat energy. And remember that heat, there's one little box full here. Flows from warmer to cooler substances. All right, so temperature, like we said, is the average kinetic energy. So my wife and I have about the same temperature. We're about 98.6 degrees Fahrenheit or 37 degrees Celsius. But I have more heat than she does because I have more mass. So heat, right, is dependent so at the same temperature, larger substances have more heat. Okay, so temperature is measured in Celsius, Fahrenheit, or Kelvin, right? But not in joules and calories. Hot or cold are relative terms of temperature. And absolute zero is in Kelvin. Again, same thing. All right. So those are heat and temperature. So remember, they're not the same thing. We'll talk about those again. We're going to talk about the kinetic molecular theory now. So the kinetic molecular theory, sometimes I'll abbreviate that to KMT, states that all matter is in constant motion. So even solid. So if I take a solid piece of metal, the particles in the metal are still vibrating back and forth. They're in constant motion. All right? And when they have a constant motion, they're rubbing together, and that causes friction, and friction causes heat. Right? Since everything has motion, right? All substances contain kinetic energy. So even if I take a single atom, right? We have the nucleus, and around the nucleus, I have electrons. Right? Those electrons, you may have learned this in your other semester. Those electrons are constantly moving within energy shells. Right? So even a single atom has kinetic energy because the electrons are in motion in that those electrons even, remember that the mass of an electron is 1. I lost my pen again. Is 1/1840th of an AMU. Right. Even electrons are very small, they still have kinetic energy, right? They still have momentum. All right. Go back to my red. All right, so since everything has motion as kinetic energies, all things can contain energy. Since kinetic energy, remember our units can be the joule, is also the measure of heat of a substance, it can describe the physical state. So let's describe physical state somewhat. All right. Here's my pen. Okay. All right. So here we go. Let me make this a little bigger for us to see. All right. So the arrangement of matter. Right. So we have solid, liquid, and gas. So some things that you probably already know. Right. So solid has a fixed volume and shape. Right. So this word fixed kind of means stuck. So the atoms in a solid are stuck in place. They are not free to move around. They're stuck, right? So these particles right here are not, this is position 1, 2, 3, 4, 5, 6. Those particles will always be in that position. That's what fixed means. And they cannot be compressed. So this is considered what they call a condensed state of matter. So this is considered condensed state of matter, because condensed means it's already compressed, right? It's not compressible. So the particles are closely packed together in an orbital arrangement. There are strong forces between them. So these we're going to call intermolecular forces, right? Even though they may not be molecules, but we'll just call them that. So there's strong forces between the particles, and the particles can only vibrate about there. So they're vibrating, that's their kinetic energy, about their fixed position. So you can say here that the kinetic energy of the substance is less than the strength of their intermolecular forces, right? So, or intermolecular attraction, sometimes called. Okay. All right. So kinetic energy is less. If kinetic energy was more, the molecules would move apart. So liquid, right, has a fixed volume, but none has a fixed shape, right? So we can measure a liquid. We can pour it in a graduated cylinder, and I can tell with the length, level of how much volume it has, but it doesn't have a fixed shape. If I take it from that graduated cylinder and I pour it on the table, it assumes the shape, but it does not fill. Okay, so it takes the shape of its container, and it's still a compressed state of matter. Right, so liquids are still a compressed state. So particles are packed closely together, but not in an orderly arrangement. So these particles are not fixed. Not fixed, but touching. Lost my pen again. Change the battery in my pen, so let's keep going. So they're orderly, they're not fixed, but which is really important when you dive in a swimming pool, because the molecules will move and touch you and come back together around you. They're held together by strong forces, but they're weaker than the solid. They can still vibrate and move. So right here we can say that kinetic energy is roughly equal to those intermolecular forces. Okay, so it's roughly equal. If we go to a gas, right? So gas does not have a fixed shape or volume, right? Gases will expand to fill their container. All right. So, and we're going to talk about that next unit with gases. And they're compressible because the molecules are not touching. All right. So particles are very far apart from each other. Right. They're not touching. There are weak forces, and the particles can vibrate, rotate, and move. Right. So we can say that here the kinetic energy is greater than the intermolecular forces. Okay, so if I want to make a liquid into a gas, I simply have to add kinetic energy. If I want to make a solid into a gas, I have to add kinetic energy. If I want to make a gas into a liquid, I have to remove kinetic energy. So that explains the state of matter. So if we take our little picture here for changes of state, so things that we already know. If I take a solid to a liquid, right, that's called melting. If I take a liquid to a solid, that's called freezing. Right, a liquid to a gas, I'm going to change this here. I don't want to say boiling. Right, I'm going to say vaporization. Right, so vaporization is the correct term from a liquid to a gas. Now there are two types of vaporization. There's evaporation and there's boiling. Evaporation is at surface. Right, so when water evaporates from my pool, it's leaving only from the surface because it gains kinetic energy from the sun, right? And that kinetic energy allows molecules to escape. So boiling occurs is, there's that. I want to just scribble. Throughout so vaporization, and then we can have evaporation or boiling, right? So sublimation is going straight from a solid to a gas, so it skips liquid. Then deposition goes straight from a gas to a solid. So an example of sublimation would be dry ice. So dry ice is solid carbon dioxide, and since carbon dioxide is not a liquid at room temperature, if I take solid carbon dioxide, it can't become a liquid, it goes straight to a gas. Deposition would be like frost. In case I decide to put those on quizzes. Alright? Fantastic. So another way to look at what I talked about above is with what they call a heating curve. Right? And you're going to do this in your lab this week. Right? So in this point here, we have solid. So this is temperature increasing. Right? This heat down here is kinetic energy. So when I have a solid, right, if this is 0, say that. So we'll call this negative 100 degrees Celsius. So if I take ice, we'll do this for water. So if I take ice, at negative 100 degrees Celsius, and I start adding kinetic energy, so this just increases temperature. Now, our melting and freezing for ice, for water, is 0 degrees Celsius. So once I get to 0 degrees Celsius, I get a phase change. So as long as I keep increasing kinetic energy, I start to melt that ice. Now you'll notice that melting and freezing occur both at 0 degrees Celsius. At this point at melting, the kinetic energy is just being used to change the phase. So this is what they call latent change in heat. So at a latent change of heat, temperature doesn't change, but heat energy changes. Okay, and you'll notice that this stays at 0 until it's completely liquid. Once we're at liquid, increasing kinetic energy increases temperature until we get to the next phase change, right? Vaporization and condensation. Again, this latent heat occurs here too, and that would be 100 degrees Celsius. If I was going back the other way, if I was taking kinetic energy out, it'd be the same thing. If this was 200 degrees Celsius up here, if I was taking energy out, it would be cooling until it got to the phase change. Then I would get latent changes in heat. All right, and we're going to talk about these again later when we get into thermochemistry. But I just wanted to introduce you to this graph. Okay. All right, so that should be enough, I think, to answer your questions for the week. All right, this should be an easy unit. Good luck, and I'll talk to you soon.